results, which means every time it's gonna hit the target with very small variation. So this is very good repeatability, also very good absolute positioning. This one, good repeatability, but absolute positioning may not be good enough. So it's missing the target all the time. This one, good positioning, but bad repeatability. This one is both bad. So this is like a student's project. Is this commercial product? Actually, usually it's in this case. So it's very difficult. So this is probably Taiwan brand. This is like a German brand, something like that. So anyway, so manufacturer is trying to produce robots like this. But think about, I can show you one example here. I'm sorry to Haiwing. I use Haiwing as an example. That doesn't mean Haiwing is bad. All manufacturers, all commercial robots has the same issue. Usually they show the repeatability. They don't show the error of absolute position. Why is that? Anyone knows why?
You can make compensation.
Say again?
You can make compensation on accuracy.
Yeah, but why don't they just claim my absolute position has an average error of 50 micron, 60 micron, or 200 micron? Why not? It's one of the specs. Okay, I'll tell you why. Because, yeah, go ahead.
Maybe because of the absolute position error is the tolerance. They can change a little bit every
position
distance, or can change, but position repeatability they want to have in the tolerance, so will be for every robot the same.
Yeah, what you're saying is kind of similar to what I want to express. The error, absolute positioning error, could be different from place to place. Later on, I will show you some experimental data. We realize when the robot is in this position, the error is like this big. Maybe in the other position, the error is in a different scale, and even different position, a different direction. So it's like you are not able to express a number to overall describe the absolute positioning error. And also, when the robot is under payload, the whole arm is going to deform a little bit everywhere. So the end effector will be pulled down a little bit more. So usually the manufacturer doesn't do that, doesn't try to measure the entire working space and then tell you averagely what will be the absolute positioning error. That doesn't help you too much. But I have discussed with some manufacturer in the past. They told me in their manual somewhere they actually did the measurement. They usually, for 6-hour robot, they will work on the extreme case where they lengthen their arm to the longest and then grasp something up to its maximum payload. So that will be the worst deforming condition. So this arm will be dropping due to the heavy weight and due to the greatest possible moment. And it will measure how much deformation will happen at the end effector and tell you, okay, this is the worst case. So based on my understanding, even for Germany robots, the worst deforming displacement at the end effector under maximum payload could be as large as 1 millimeter. Not 1 millimeter, 1 centimeter. So it's in the scale of 10 millimeters. So it's quite large. However, even with this positioning error, for simple pick and place, does it matter? maybe not so much. Because even for human, we don't care too much about how our hands should be precisely positioned so I can properly grasp. So, however, but for precise applications such as tightening a screw or insert something into a hole with very small tolerance, for that kind of precision mission, positioning will be very important. And later on, I will show you how we compensate the positioning error. There are, again, multiple ways. We are not the only way. This is not the only way. Okay, so if you want to position your robot, you need to do some measurement. You need to know where your robot is. So here I'm showing you 4 different ways. The first one is laser interferometer. It's a really good tool. Basically, apply one laser beam onto somewhere on the robot, and then by the reflection of the laser, the interferometer will figure out the distance between the device measurement tool itself and the target. So when you have a laser beam hitting the robot arm, then you can hit 0. Okay, now it's 0 position. When you move toward out away from the device by, for example, 10 centimeter, the device tells you, okay, 10 centimeter. So laser is a really good tool. It gives you accuracy in 1 micron. The repeatability of the robot is usually 20, 30 micron. So if you, the laser is 10th order more precise, one order more precise than your positioning error. So laser is actually quite good for determining the robot position. However, it's not super cheap. In Taiwanese dollars, maybe 300,000 or 500,000 Taiwanese dollars, or if you have better ones, it could be up to 1 million. So usually in universities, there's probably 1 or 2 laser interferometers, maybe in some of the labs, which are working on metrology or optical research. Or maybe the university or the department has some measurement labs. So maybe they have, I don't think all the universities has one. So laser probably is not your everyday tool. It's not easy to get, but at least it's affordable by the university. In some company they have. I will let you know why it's not convenient for 3D positioning. So there is an even better tool. It's called a laser tracker. So what is it? Basically, you need 3 sets of this kind of laser interferometer. So you have 3 laser beams and then concentrating on a object in the 3D space. And the reflection goes back to the receiver. So basically you have 3 linear measurements from the sensor to the object with 3 precise linear measurements in the scale of micrometer. You then can compute the exact 3D position in probably microscale or tens of microscale. That's called the laser tracker. Laser tracker is very expensive, so probably 10 times more expensive than the laser interferometer. Well, I have heard there are laser trackers in the price of 5 million or 10 million, and probably even in precision manufacturing companies, they don't have it. In some of the famous aerospace manufacturer, maybe they have one. Or in some of the, I know in E3 they have one, something like that. So it's very expensive. I think I have seen that once. I have never upgraded. So just for you to know. How about stereo vision? So your cell phone has stereo vision. But if you try to use your cell phone and with some app, you try to measure some features at the corner and then try to measure the dimension of the door, it gives you very poor accuracy of the dimension of the door. The error could be as large as centimeters, and if you try to measure geometry far away from your camera, it could be having errors in meters. So definitely not good for robots. And the last one is a very interesting application that we have done several years ago. It's based on some kind of encoder. I will let you know when we move on to the slides. So this is the method one, laser interferometer. So this is the device. It has a laser beam coming out of the device, and there is a optical a component right here. It's called a splitter. So when the laser hits the splitter, it will be split into two beams of laser. One penetrates through, the other one reflects back to the receiver. So one laser being split into two, one goes forward, one goes backward. So the one goes through, comes to here. This is a reflector only. So that beam of laser hits this object, this optical component, and reflects back to the splitter. And the coming back laser directly penetrates through and then goes back to the receiver. So one beam coming out of the device, two beams coming back. One comes back earlier, the other one comes back later. Because of the time difference, the device is able to measure its position from the device to the reflector. So using that trick. However, this measurement can be done only if you are able to have all the laser movements staying on the same line all the time. So later on, if you want to measure the exact position of this device on the robot arm, you want to move around on the robot, and let's say you want the robot to move from here to the other place by 10 centimeters. You want to use an optical device to figure out, is it 10 or 9.9 or 10.01? This is a way, but that movement has to stay on the same line as the laser beam. That's why this experiment is not very convenient. Okay? If you would like to use more lasers, like a laser in a line, or even laser in a 2D space, that's very expensive. Okay? I know in fluidic applications, they sometimes use a string of laser. They try to study what's happening at the cross-section of liquid stream. So they have like a array of lasers. Then it's very expensive. So for simple arrangement like this, you probably can only focus on one linear motion. And if you want to study the exact positions of a robot in some other places, you may need to move around your laser beam so that the laser beam matches with your motion. So you may need to take your linear motions for multiple times every time you set up your laser beam, try to align properly. So it's very time consuming. And of course, if you have more optical components and figure out how you can control the laser beams with a bunch of optical components, maybe it's doable. You don't need to move your laser, because moving your laser is not, that changes the coordinate system. So with the help of a lot more of the optical components, maybe you don't need to move the laser, but that's too much for my lab. So we just stay with this. So at the time, we have a group of students who were taking linear measurements of linear motions, and they basically take linear measurements line by line, and they sample the working space. What we want to do is try to figure out how accurate the robot is inside the working space. They don't even care about the backside, because we are just trying to figure out what's the error in some space in the front. When we are working on it, we don't care about the backside. We don't need to worry about errors outside of our working space. Okay, so it took them so long to complete all the measurement, because every day in the morning they need to set up the laser interferometer, and then they take one linear measurement. So that probably took them one morning. So I asked them to take multiple linear measurements in the space. Probably took them 1 month to complete all the measurements. So it's very time consuming. That's why we move on to another trick. Here is so-called the cable encoder. So what's a cable encoder? I think my lab still has it, but I'm not sure if my students are using it. Maybe somewhere in the storage. But if you're interested, we can figure out where it is. So you can treat it as a digital ruler, but it's not a ruler. It's a cable. It's a metal cable. So the cable comes out. You can pull it, and there is a like a spiral spring inside. So it pulls the cable back if you release it. And for the center axis right here, there's an encoder. So if you pull the cable away for 10 centimeters, the encoder will be rotating for a certain angle. So there will be a digital information coming back to the computer telling you how long you have pulled out the cable. So by using this trick, you can take a measurement from this point to somewhere here, right? And whenever your robot moves, you are always taking the measurements. But the drawback of this setup is there are always 3 cables hooking up to the space. So the cables could be affecting your motion. So I think our setup was only good for calibration. So maybe at the beginning of your robot operation, you can do this calibration. Once it's done, you can remove all the measurement tools. Okay, let me tell you what's the mathematics behind it. So you have multiple cables. Okay. We have 3 cables. You know the position of the encoder, and you will hook up to like a connection plate. So this is a P-point. So OI and TI will be the length. The length from OI to TI will be the length of the cable. And this plate was made by the student, so the vector from any vector to the P is known. So D is a vector from E to P. Any vector is unknown. So basically, I assign any vector coordinate to the robot. The robot will move to somewhere. So at this point, we only know the coordinate that was given to the robot. But we don't know the real coordinate. The real coordinate will be measured by 3 tables and using some math, try to calculate what's the real coordinate. So that's it. So by this equation, unknown n vector coordinate, known d vector, known coordinate of the encoder, measured length for every position of the robot. So that's one equation, but we have 3 unknowns, right? The n vector has x, y, and z. So we just need 3 tables. So there's an exact solution that can be done. The calculation was inspired by GPS position. So this method is called trilateration. So if you Google multilateration or trilateration, that's the mathematics for GPS position. So basically, our cell phone always has distance measurement from itself with several satellites. So why does our app is being able to know where it is? Because it has been doing trilateration or multilateration all the time. Okay, so this is the exact map, same map. So go figure it out. So we did that. So the idea is, in the working space, we care about measuring the error in the space, and later on we can figure out how to correct the coordinate. So we will be sampling the positions by 364 points. And then the idea is, if I assign a coordinate to a robot, so we expect the robot to move to a certain position. However, in fact, it could be moving to a different position. So we use a tool to measure the error factor. That's the idea. Okay? So if we can do that, concept-wise, we ask the robot to move to here, but in fact it moves to the tip of the green arrow. So we use some tool to measure it, either by laser or by cable. So we compute the green vector. So we will, by sampling the space, we will have a bunch of error vectors. What you can do next, we can have an error field. So if I know the error field in the working space, in the future, whenever I want to move to anywhere inside the working space, I know exactly, I can estimate the error vector right at the point. Then I can use it to correct the position. So we use a statistical trick. It's a parametric modeling trick. The method is called preview. So basically it's regression, okay? But it's not the usual regression. Well, the regression you have learned usually is in the form of polynomial. But the problem is we don't even know the order of the robot error in the space. So we don't know, should we use cubic polynomial or 4th order or 5th order? We just have no idea. So this method is actually a very well-known, well-developed method in the design field. So whenever they handle nonlinear regression, they sometimes use this method. So this method is an exponential-based method. So if you're interested, you can take a note about this the name of this method, preview. Okay. So if one day you are dealing with nonlinear regression and you just have no idea what kind of polynomial model you should use or any known form that you should use, you can try to. Okay. It's not very easy, but if you are able to do it, complete it in your graduate research, I think you can use a chapter to describe quickly. So it's good for publication. Anyway, so in order to model this exponential functions, there are some shape parameters to be determined. The shape parameters will be optimally determined so that the geometry is the best fit to the experimental data. So over here, the semi-variogram is for determining the optimal shape parameter. And all the small circles are real, so-called semi-variogram based on real measurements. And the curve basically is the fitted model, basically a part of 3D. If you can see pretty well fitting between the curve and the dots, that means you found the optimal parameter. Okay? And of course, there are cases where Krillin was not able to fit the data well enough. So go figure out. There are some famous methods in Krillin. Is a part of the Krillin. Let me think of what's the name of it. It has been a while, so I kind of forget the name. Krillin curve. Because you may not know about that method more. Forget about the name. Okay, sorry, I cannot think of it right now. But go figure it out. If one day you need to use it. Anyway, once you have it, this is how the regression model looks like. So we use it to model the error field in the working space. But there are 3 dimensions. So one regression model for each dimension. So over here, if you take a look at this one, this is the normalized x, y, and z space, basically the space in front of the robot. And all these nonlinear curves basically are the predicting model determined earlier. So if you choose any arbitrary point inside the working space, you can see the measurement here. You can see, oh, along x direction there are errors like here, or 2 millimeters, or negative 3 millimeters. So the colors are representing the error along x direction in that particular position. Okay, and we have a error field for y direction as well. So in this particular experiment, we realize errors along x is larger. Errors along y is smaller. So I think in our experiment, probably left and right is x. So y probably is here, if I remember right. So for the robot, based on our experiments, the error along horizontal direction is greater than forward direction. Okay? So, and from here you can see how nonlinear the error along y is. you probably cannot find any polynomial function that can describe this kind of nonlinear error. So how come we only have x and y? There's no z. Because those were pre-models based on the laser measure, not the cable yet. Those are the ones built based on laser measurement. And remember, we try to take laser measurements along the line, but we didn't know how to take laser measurements from top to bottom. Do we move the laser parameter to the top and then take measurements from the sky? Actually, I have spoken to some professors from in optical measurements. They said what you should do is you need some kind of optics to help you to change the direction of the laser going up, going left, and then going down. So that means you need to set up a lot of optical components. So it's too troublesome for us. That's why we didn't take Z measurements for this particular model. But for the cable encoder, we did. I will show you correction based on laser measurement. So from here, the idea is, initially when I asked the robot to move a certain coordinate, in fact, it will move to this blue coordinate, so we took measurements. So now we just need to give the robot some fake coordinate, like here. Tell the robot to go here due to the error of this particular position, and then the robot will really move to some position that we desire. So is it easy? Can we just easily use the error right here and then just minus the error so we can ask the robot to move to this position? Actually, no, because the error vectors in the space is very nonlinear. So the error vector from this point and the error vector from this point are not the same direction. So we cannot just, if I want to go here, I just use the measurement that we had and then minus the error vector. So we end up with some position here, right? But if we expect the robot to move to this position, at the end, due to the error at this new position, we may end up with some result right here, and it's not going to the position that we desired. So this specific method was designed in such a way, and I can show you some experimental data. So this is the desired position. Like I said, we didn't focus on Z because we didn't take Z laser measurement. So we only work on some planar motion. We asked the robot to move some positions along some plane, but in fact, the robot goes to some other places with certain errors. Right here, the error could be as large as 1.2 millimeters. Okay, if you think that's not good enough, then you can apply our methodology. This is the coordinate after correction. From there, you can see the errors are very small. The largest is only 30 micron. How can we achieve that? Because we use the so accurate measurement from laser, so that the error field was really precisely measured. Like here, error reduced 97%. We did the same thing in a different plane. Again, the largest error we had was only 15 micron, also very precise. But this is not working for Z. Okay, I think I have hot points for Z code. I have hot points for cable. Let me figure out what it is. Give me a sec. I think it would be interesting for you to know what's going to happen if we try to position using the cable. Figure out. Several years ago, I reduced my slide. This one. Okay. So in 2020. I think I will hold this too large. I will download the PowerPoint. Okay, so that was the time we had. Okay. So how about the cable? So at the time we tried to use the cable encoder as well, and then we realized, okay, by the way, if you're interested about the cable encoder, here are the spec and how it looks like. So if you want, you can take a picture. We use the laser to measure how accurate the cable encoder was, and the longest measurement the cable was able to make was 700 millimeter, and this shows the error of the cable. So the cable was not super precise. The error was as large as 1 millimeter. So how can you use a tool that has 1 millimeter error to measure the robot? You cannot. So what can we do? We can try to reduce the error of the cable first. So my graduate student, he used the laser interferometer to measure the cable, to figure out the error inside the cable. And he built a second layer of the Kriging model, like this. So what's this? At different cable angles and with different encoder measurements taken from the device. Here's the measurement that was found by the laser. The whole space was modeled by Kriging. So now, at any angle within 40 degrees to 90 degrees at any encoder measurement, I know what's the error. That's what it did. So with this modeling, he was able to reduce the cable encoder accuracy from 1 millimeter to 0.2. So he first used some mathematics to improve the accuracy of the measurement tool, then use it to measure the robot. And in fact, he has to model this 3 times because he has 3 different cable encoders. Each cable encoder is different. So he did this 3 times. And then he used it to model the error of the robot in XYZ space. Now you can see this is the error in X, in Y, and in Z. Okay, so cable encoder accuracy was reduced from 1 millimeter to 0.2, and the 3 cable measurement for the robot can be and use it to correct the robot. You can have robot accuracy from more than 1 millimeter to 0.5. So at least it's a kind of improvement. Now you can have 0.5 millimeter accuracy for the robot everywhere without using laser. Just use the cable. Okay? But it's not as accurate as the laser. So that's what he did. I think I had a video somewhere here. Okay. We can take a look at the video. Yeah. So this is nothing. Yeah. So at the beginning, there is a laser interferometer outside of the camera. So coming to here, this is a splitter, this is a reflector, and this is a computer that gets readings from the laser interferometer. So starting from 0, basically 0 micron, right? This is 1 micron, starting from 1 micron. Okay. So he asked the robot to move toward the left by 700 millimeter. You will see 698.99. So the error is close to 699, right? So the error is around 1 millimeter by just linear motion. So go back to its own position. After coming back, we use this opportunity to test repeatability. Starting from the beginning, move forward, and then come back, you will see around 10 micron of error. Okay, so 10 micron is basically under the spec repeatability. Spec says the repeatability should be better than around 20 or 30 micron. So this is 12 micron, which is good. So now we apply the correction by reading and start to move to some desired position. After this correction, all the positions are more accurate. So we now move to position of 250, and you can see the error is 3 micron. Now move to 450 again. Yes. The error was around 9 micron. Finally move to 700. Earlier it was 699. Now it is only 30 micron of error. So after correction is precise. So we did what we talked about on the blackboard, the student calibrate the space with a camera, and there is a small object with a hole. So the student will use some image processing to determine the random position of the hole on the object. So with that position, we will match the camera coordinate with the robot, ask the robot to pick up a small cylinder and put it into the small hole. Okay? And the small cylinder and the small hole has a tolerance less than 1 millimeter. So if you have inaccuracy of 1 millimeter, you are not able to insert a pin. So that was what he did. Okay. So he randomly put the object underneath the camera, some image processing to identify the position of the hole, and then, that video was 10 years ago. So the robot picked up a cylinder and then insert into the hole. Without any problem. Okay? So if there's no correction, if you only did camera and robot calibration, there still exists some positioning error of the robot itself. So one day you assign a coordinate to the robot, maybe the robot is not able to move to the exact position. It has 1 millimeter of error. Then you are not able to get it. Okay. This is a video to show how you can build a robot by yourself. So the graduate student built a robot. Like I said earlier, he used metal plates to build a robot. So the repeatability was not good. So this is a 4 degree of freedom robot. It's commonly used for bigger plates in the factory because the end effector is always parallel to the floor. So if you want to build a robot from scratch, here's one example. So the student participated in a competition to work on this. The mechatronic system was provided by the company, the competition organizer. Of course, you need to pay for something. And then he is hooking up the power and the driver. And also, this company has a controller that is in the user in the panel. The controller is in the panel. So the company used a digital panel to assign robot coordinates. Those information will be passed to the driver. The driver will translate the command and rotate the robot. So from here you can see, from there, you can see they have a digital panel and the controller, I think they are having a digital controller inside. Controller sends commands to the driver. Driver basically activates the motor motion. You can see they are rotating. Okay? So, one story about this student. I think he participated in the competition in the summer, one of the summer. And he got this task probably in January. So he has one semester, 6 months, let's say 6 months, to complete the whole thing. So I can tell you the robot is doable within half of a year because this person has done it. So he, in the beginning, he showed some CAD design somewhere here. So once he realized, okay, this mechanism is walkable, the end effector is always parallel to the surface. Okay, he sent out some requests to the outside manufacturer to produce the parts. I think he used the machine shop to manufacture some parts all by himself, but many of the rest were done by the outside manufacturer. So after he completed the mechatronic system, probably took him 1 or 2 months, all the metal parts were done. So then it will be the time to assemble it. So like I said, most of the components were metal plates and connected by some supporting structures at the middle, which is not super strong. So the metal plates could be bending when it's moving. Like they only have this cylindrical support at the middle. Not very strong. One of the reasons why he did this design is because to have bulkier structure is going to be very expensive. Okay, so if he designed all these by plates, it's much cheaper. So I didn't ask him to make stronger geometries. So this is how the robot looks like, and I think all 3 motors rotate at the same time. This one, and this one, allowing this geometry, any vector to move to any position while remains parallel to the floor. Okay. Another interesting example for hand-eye calibration is this one. It's an undergraduate project, and as you can see, it's using our Epson Robotics lab to do some project, where the student, I think the undergraduate student, took some pictures from the top and applied some image processing to realize the position of the yellow ball, and then use the robot to mimic soccer ball kicking. So some calculation needs to be done to figure out the position of the robot and then orientation of the kick, the plate right here, and then also moving direction. So you can hit the target all the time. So one interesting example. The other one is also relying on hand-eye calibration. So this is a graduate study where we want to have inspection of objects on random surface without stopping the production line. So you know in Taiwanese production line, there's always the long line and there are stations and stations. if a part needs to stop somewhere, and for a certain process, time is wasting over there. So if you can do something while it's moving, it's gonna save some time. So let's say you save 5% of time. That's money. Okay? So the inspiration came from that purpose. So what was done was on the top there's a 3D camera which will study the random surface of the object and then try to figure out the normal vector. So no matter where you place the object, the normal vector will be determined by the 3D camera. Once you realize what's the normal, based on known speed of the conveyor, the student can figure out where exactly the end effector should be so that the camera on the hand will be facing the surface perpendicular to the surface, so you can do inspection perpendicular. Sometimes you need to face to the surface perpendicularly so you can do proper measure. So the purpose was to figure out the normal vector of the random placed space, random placed object, and then once you realize it, that normal vector will be moving with the conveyor. So at certain point, the robot is desired to move to this position and then move with the object. So there will be a small window, a reachable space for the reachable space of the robot. So once the object moves into the working space, the robot will move to here and then follow until it can no longer reach out. So inside this window, the robot can do something. So within this window, supposedly, the relative speed between the camera and the object is 0. So you are supposed, so it's like an object is having no speed for the camera. So you can do a pretty good inspection. If possible, you can probably do some insertion. So maybe there's a container, and if you want to put something, even if it's moving, maybe you can move with it and then place it. Okay, so that was the project. And you can see this is the live feed of the inspection where the camera right here is capturing the circle on top of the surface, and even though the object is moving, the inspection is having pretty good stability. Okay. But not all, it's slightly shifting. So there are still some measurement error somewhere. Okay. I think I have one more. Maybe this one. So, in the project, you probably need to calibrate some camera and the robot. I have shown you some applications. So please be aware your robot manufacturer could be having some error. Okay? So how do you correct the error? What I show you is one way. Either use laser or whatever trick or cable. You can try to make this as accurate as possible. For the camera itself, you know, for all kinds of optical device, there is always distortion. Okay, so people try to use checkerboard approach to apply some correction parameters to deform the detection space because of the detected space is distorted. So they try to multiply the result with certain correction matrix. So they can distort the distorted space back to a straight coordinate. But usually this kind of correction has to be done at different distance. So you can say if this is the camera, okay, if this is the camera, and if you're viewing something, if you have a box, okay, what you really see in the camera is a distorted box, slightly distorted. Okay? Is it this way or the other way? Oh, maybe the other way. So usually if I have a camera, the student on the side has a wider face, right? Because the camera in angle has a distortion. Right? So what you get actually is fatter than usual. So you need to multiply some kind of correction to shrink the space in a certain way. Okay, so usually people use something called a checkerboard approach. So they have a standardized checkerboard, and then you can Google for how to do it. So if you can do that, then you have a more precise camera. Then the object coordinate underneath the camera should be more accurate. So if you can make this more precise, the transformation that you get in the end should do a good job, should be doing a good job. Okay, so that's what I want to introduce today. I didn't take a break, so I guess I can finish the course early. Okay, any questions? I hope this is helpful for your project. Okay. Was there any? Do you want to comment anything? No. Okay. Any questions from the student? Do I need to assign one? Nothing.
Yeah.
Okay. Good. Okay, so that's it. See you next time. Right.